A wonderful Friday. My name is Khaled, and today, inshallah, we'll be completing Peter's lectures. I don't know if everyone's here. There's 48 people here currently, all of us included. Okay. Uh, I'm not sure if we should wait, but uh, I think it's just good to start. We were already any kind of 6 minutes, kind of late. So, all right. I think all of you can hear me. I can see the chat. Okay. So with that said, let's just go ahead and start. Let me just put the chat on the slide. Now, I know what you're all thinking. Hey, Khaled, why are you starting on sampling distribution? We finished this lecture. Actually, no, we didn't finish this. I skipped over something because this was part of the confidence interval lecture. That's why we skipped it last time, right? It wasn't on your midterm. But I don't want to start with confidence interval without kind of giving you just a brief little idea from this lecture. So I'm just gonna give a quick revision because I know maybe most of you may have forgotten a lot of the things here. But yeah, so let's start with this revision. It keeps telling me admits and it's blocking the whole screen. Okay, so remember this part of the lecture where we were saying how to calculate all this stuff. The whole where's the pen? The whole z equals x bar yada 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 minus population mean minus mu and then over SEM or whatever we use. Remember this part, right? And then we find based on whatever value they gave us like 110 or maybe here like 107. Then they're like find this value, the 11.5. We find the z yada yada yada. We remember this stuff, right? We don't need to go over it because this is going to take like an hour to go over it. Here they're explaining a new principle. They're telling you, well, you know what? Let's say we have a mean. Let's say we have, for example, this distribution, and we have this mean here. And I'm going to use the same numbers they give us. Let's say this mean was 105. And then they say, hey, we want to know the limits. For example, we want to know at what points are there going to be, for example, 5% of the data outside of those 2 points. For example, at this point and this point, we want here, for example, 2.5%. I'm not gonna 2.5, and then here the same thing, 2.5%. How do we quickly find out what these two values are, right? And then he tells you what's the importance of that. Before we go into that, let's just try and find out how we can do this. Well, a very simple idea would just be to take this mean and go 2 standard deviations this way and 2 standard deviations this way. And there you go. You found the limits on both sides. And this is really important. This is really important. We'll get into it just in a minute. Let me just find out what exactly these numbers are. So to go 2 standard deviations to the right, we have to use a z of 1.96 because recall this will give us 2.5, a p-value of 2.5%. And we obviously multiply that with the standard deviations because z is the number of standard deviations, right? So we multiply that by the standard deviations. In this case, it's the standard error, right? It's the same thing. It's just divided by radical n. And then we're gonna go like I said, we're gonna go one direction to the right once, and then one direction to the left once. So here, when you add it to 105, we're going right, and it gives us the value of 109.9. So this exact point is 109.9, and this exact point, if you minus it from 105, it becomes 100.1. We're still not explaining anything new. This should be something that you all kind of understand, and you all were tested on in the midterm, and that you all sort of have at least somewhat of an understanding of. But now here's the important part. Okay, so what? We now know that these are the limits. What's the importance of that? Well, why do we care about this? Well, here's why you should care about this. Now you don't need to think anymore. You don't need to do z anymore. You don't need to do anything anymore. If I tell you I got a new sample and their mean is 115, and I tell you, is this significant? Is this statistically significant? You would instantly tell me, yes, it is. Why? Because you know for a fact that these values cover 95% of the data. So anything from 100.1 to 109.9 should cover 95% of the data. So if I give you any number at all, outside of these 2 points, you should be able to quickly tell me, like don't even think, just quickly tell me yeah, it's significant. If I give you 90, oh, it's significant. If I give you 99, oh, it's significant. If I give you 109, 0.91, it's significant because it's beyond 109.9, right? So that's the importance of this. And he goes on to it and saying what might be the use of it. And then he goes into why 5% and all that stuff. But that's the use of it. That's the use of it. The use of it is that we can immediately make an interval, right? This circle is our mean, and then this, for example, is going to be 100. Let's say this, just to make it simple. Let's say this is 100 and let me move the chat. This is 109, just to make it simple. 109, and this is 101, just to make it simple. And then this is the 105. So this is the mean. So immediately, if I tell you, for example, hey, is 104 significant? Well, no, because it's within this. It's within this entire interval. If I tell you, is 110 significant? Yes, it is statistically significant because, hey, it's outside this interval. And that, in a nutshell, is confidence intervals. Now, there's a lot of understanding behind them, a lot of theory behind it, and we're going to go into it. But this is just to give you a little brief idea, okay? And with that, we've covered the part from the sampling distribution lecture. So now officially the crash course did start. So I'm gonna remove the PowerPoint, and since it officially started, I have to always tell you the same thing that I say at the start of every single crash course. Um, Especially now because this this final crash course, every lecture is literally based upon the other lecture. So the concepts that you will now learn from confidence interval, you will see them again in hypothesis testing. You will see them again in comparison of means. You will see them again in ANOVA. You will see them again over and over and over again. So if you don't understand confidence interval, if you feel like you have to ask a question and you're scared that you're going to slow us down, don't be scared that you're going to slow us down, because there's no such thing as slowing us down. If you don't understand it, you might as well just leave the call, because you're not going to understand anything after this. So if you have a question, as always, ask it in the chat, and I will, deal with every single question that comes, and I will try and sort of facilitate all the questions that come, so that everyone understands that we're all at the same sort of level. I'm not teaching only half the class, I'm teaching all of you. All right, so confidence intervals. Before we absolutely start, let me give you a brief idea of what we're going to be doing today. Ideally, we should finish by 8:30, but that might not happen. I hope it happens, but it might not happen. It might not happen. We're going to be covering confidence interval, which, it's not really that difficult. But then we have a very, very devilish lecture after it called hypothesis testing. This is the hardest lecture in all of biostats for second year. And I say it's very hard, but it's just one concept. And if you understand it, khalas, you can understand all the theory behind it. Then we have two other lectures, which are semi-difficult. So if we really just pass hypothesis testing, the rest is going to be easy, inshallah. So with that said, let me get this working. And let me share screen. The z-value of 1.96 is fixed for 95% of the data. No, listen, the z-value, I mean, you're right, but you're skipping way ahead. The z-value is fixed for a p-value of 2.5%. So if you take 2.5% from the right side and left side, then it's going to be 95%. Yeah, that's what you meant. Yeah, exactly. So I'm just making it sure. Yeah, you're welcome. Okay, so let me share screen. But yeah, just to make matters simple, you're right. Z-value 1.96 will lead us eventually to 95% of the data eventually. Okay, so confidence interval. This is a bit difficult. It's not really that hard to see any. It requires some thinking. So like we mentioned previously, I showed you that, if we have a mean here at, where's my mouse? We have a mean here at 105. We go 2 standard deviations this way and then 2 standard deviations this way, we can get the limits. The limits are referred to as the ends of the confidence interval. In this case, it was 109.9 and 101.1, which are here. I drew them right here and right here. Right now, the beauty of this is that anytime now you make a mean, like let's say I got a sample and my sample mean is 112, you immediately know that this 112 is significant. Let me get the chats. How do I get the chats? There we go. Nope, it's not coming up. There we go. Now it's coming. All right, so now you don't really need to do all the Z stuff and then what's the p-value, yada, yada, yada. You can just start eyeballing it. And this is what most journals or most articles do. You might see that they present this sort of figure where they say, hey, this is our confidence interval. And then they put like the mean, this is the confidence interval. They do it sort of vertically as opposed to horizontally. Sometimes horizontally, sometimes vertically. It doesn't really matter. And they say, hey, oh, the mean is here. So look, hey, this confidence interval, it's not touching this mean. So immediately, you just clicks a bell inside your mind. You're like, oh, this sample is statistically significant. That's the beauty of confidence interval. You don't need to calculate. Immediately, what you visually see is going to help you. So it's useful if we collected more samples, yada, yada, yada. We would then test if we would then see if the mean value lay within the limits. Yeah, same exact thing I'm telling you. You don't really need to calculate anything. You just see whether this mean is within the actual confidence interval or not. And if it's not including it, then you say it's significant. If it is including it, you say it's not significant. It is more complicated than that, and we will see it as we keep going with the slides. So here he gives you an example. It's the same exact example, only difference is different numbers. Here the limits are 105.1, 114.9, same exact thing. And he basically is just throwing this other example at you just to show you how the numbers can be different, yada, yada, yada. Here's more examples, more stuff for you to practice. But now let's think a little, okay? This confidence interval, they could be different. Some confidence intervals could be very narrow. Some confidence intervals could be very wide, okay? Now, how can we, for example, determine or sometimes factor in our, how can we change a confidence interval, make it narrower or wider? The easiest thing we can do is change the sample, because if we change the sample size, I mean, because if you look at the formula, it has SEM inside. And what is SEM? It's standard deviation. Again, we don't really change the sample mean. We just collect it. We can't really change the standard deviation. We just collect it, right? But what we can change is the ends, right? So a standard error, if you recall, was standard deviation divided by the square root of n. We can actually change n. We can collect more data. So if n is high, because it's in the denominator, eventually this entire number will be lower, meaning that the amount that you will add or subtract to x bar will be lower, meaning that the interval will be narrower. Again, I'm going to repeat this because it's really important. I need to get the chat up. This is, again, really important. There are still some questions. I'll just repeat this one more time because this is incredibly important. Okay, then I'll see the questions. If you collect more data, recall that SCM has in the denominator square root n. So if you raise this n, if you collect more data, as opposed to 100, you collect 1,000, then overall this entire number to the right of x bar is going to be smaller. Therefore, for example, if you add, let's say x bar was 100, if you add 3 as opposed to 5, then the possibility of stretching out the confidence interval it decreases, right? Instead of going 5 units out, you go only 3 units out. So instead of, for example, going 5 units, you only go 3 units. So, and same thing for the left side. If instead of going 5 units, you go 3 units. So notice by collecting more data, your confidence interval gets narrower. This is the exact principle in the next slide. Notice how as n increases, this number on the right keeps decreasing and decreasing and decreasing and decreasing. And this corresponds to a decrease in the length of the confidence interval, right? And he gives you this very nice figure that you need to really commit to your understanding, that by raising the sample size, you pretty much make a narrower and more precise confidence interval. Now let's take some questions and let's see what you guys are asking. Okay. So let's see. So the z value of 1.9, yeah, we already answered this. Are we calculating the confidence interval of the sample within the population or the population itself? Okay. So in terms of populations and all this, here what we're doing, I want you always to remember that when we make a confidence interval, it is always from a sample mean. So we take a sample, then we find that sample's mean, then we go 2 standard deviations to the right, 2 standard deviations to the left. That is the confidence interval for our sample, right? We'll go more into how this links to the population, but for the time being, just understand it as is, right? Don't jump ahead to what about populations and the stuff. We'll get to it when we reach to it. But for now, a confidence interval that we're calculating right here, is a representation of 95% of the data within a sample, and we can sort of go and add more knowledge onto that. So I know this is such a stupid question, but I don't understand why do they mean by significant or insignificant. So we talked about this in the midterm. So significant means that your p-value is less than point or less than 5%, which is 0.05, right? So it's if it's less than 5%, it means that you were very lucky to get this p-value. So you pretty much have two options: whether you trust that p-value and say that, hey, maybe I got lucky, or you say, hey, the drug really works or doesn't work, yada yada yada. We'll talk more about significant and not significant in hypothesis testing. But for now, whenever I say significant, it means p-value is less than 5%. Just memorize it, memorize this for now, because you'll understand it when we talk about hypothesis testing. This isn't really the lecture that we talk about significant and not significant in detail. Yeah, it's significant when it's outside the interval and significant when it's inside. Yes. Yes, I got this one, but I mean, well, if we got a significant, doesn't that mean we can't use the sample? Yeah, so Lanani, you're jumping to a point that's mentioned in this slide, in this lecture, right? This lecture, you might be referring to this point that, hey, this did not touch the mean, so we can't use this. I'll talk about this. You guys are jumping. Just understand what we're talking about so far. So long as you understand the limits and you understand this idea that what's useful about the limits, it's that, oh, if a number was outside the limit, then it's significant. If a number is within the limit, then it's not significant. This so far, I'm happy if you know that. We will talk more about theory. Don't jump ahead. We'll talk more about theory. But for the time being, this is the only concept we really talked about. And if you understand that, we'll add more onto it as we keep going on. Now, the other thing that we talked about was n. If we increase n, the confidence interval gets narrower, and I hope all of you really understand that well. Okay. There's a small problem I'm facing, which is that the chat keeps disappearing when I click on the slide, which is the same exact problem that I kept facing in the last one. Let me just stop the share very quickly and then do it again.
Doctor, if you don't mind me making a suggestion.
Oh, sorry, I didn't hear you. Yes?
How about someone volunteers to read the chat for you just so we avoid the chat going down?
No, it's fine. It's fine now. I know how to
It's
fix it.
fine?
It's just I keep messing it up. It's a very long story. If I press share screen on the actual PowerPoint in the thing, it doesn't go away. So it's now good. I can see the chat. So increase n, decrease the SEM. Yes, increasing the n. Yeah, and we talked about this. When you increase n, your standard error should decrease, right? And this indicates that the variability decreases because the standard deviation, the standard deviation doesn't decrease. The standard error as a whole decreases, and this indicates that the entire distribution becomes narrower. And you're going to hear this a lot. When you increase n, a lot of things become narrower. Confidence intervals, the distribution, so on and so forth. You will hear this a lot. Whenever you increase n, you will get a decrease in standard error. You will get narrower curves, so on and so forth. Narrower confidence intervals, so on and so forth. But yeah, this is really important. We all understand this. Now, what does it mean? Well, what is the meaning exactly of when we have a confidence interval that, for example, let's say from 0 to, for example, 5, and here is -5. So what does this confidence interval really mean? It means that from this sample that we got, where the confidence interval goes from -5 to 5, we don't really need to know where exactly the population mean is. We are 95% sure that the population mean is somewhere between these 2 points. Now you might say, oh, that's pretty weak, right? 95%, there's a 5% chance of you missing it. But actually, 95% of a 95% chance of knowing where the population mean is incredible. It's absolutely incredible, because as you will find out with the upcoming lectures when we talk about comparison of means, we don't know what the population mean is. So having tools like this that can dictate to us a possibility such as a 95% chance of knowing where the population mean could be, that's incredibly powerful. Because maybe the population mean here is -2. Maybe it's -2, but we don't know that. What we can do is get a sample, make a confidence interval, a 95% confidence interval, then we'd be 95% sure that the true population mean, that we don't know what it is somewhere between these 2 points, right? And that is how you understand confidence interval, right? So far, I don't want you to jump ahead. I don't want you to go anywhere. This is the only concept so far that has been shared about a population. Um, Usually we don't know what a population is. I'm going to repeat it. Usually we don't know what a population mean is, but we can estimate where it could be. Now, how good is our estimation? We can be 95% sure within a given interval that we made from our sample that the true population mean lies within this interval. As you said, the 2.5, 1.9. Okay, because you said, I don't get your question, because you said the 2.5, I'm still confused as to how we calculate these limits when finding the numbers that contain 95% of the data. Okay, we're gonna do this example. We're gonna do this example that he gave us, this extra example. So what did let me erase all the ink on the slide. I'm sorry if I'm very slow with drawing, because I'm actually using my touchpad, not my mouse. My mouse it broke. So let's do this example. He gives you the answer, but do we have the example, just the numbers? Okay, let's just do the example, and I'll show you how he got these numbers exactly. So when we want a 95% confidence interval, you need to memorize a certain number. You need to memorize that z is always 1.96. Okay, so you mentioned in the question that I'm confused because you said that 2.5 and 1.96 are not universal. No, they are universal. Z equals 1.96 will always give you a p-value of 2.5. Now, why am I picking 2.5, not 5%? Because we need 2.5 on the right side and 2.5 on the left side. That will give us a total of 5% outside the interval, therefore having 95% within the interval. So now what do we do? Well, we have a mean, a sample mean. Let's say our sample mean in this case was 110. So we have 110 right in the middle, all right? Now we need to go 2 standard deviations, or 2 standard errors in this case, because we have a sample. And let's say, just for to give more given, our sample standard error, I don't know what it is in this example, but let's just say it was 16, okay? It might not give us the exact points that he had, but I don't know what the standard error is here. Did he mention it? No, I don't think he. I think he mentioned it in like the previous slides, but I'm too lazy to go back to the previous slides. So let's say the standard error was, to make it simple, let's say this entire number. Did he? Oh, he did mention it right here. This entire number was 2.5, okay? So what he would do is he would say, okay, I want to add to this mean, this sample mean that I have, I want to add to it, to go to the right side, z times SEM, right? And this will give us 4.9, right? This will be the 4.9 that he got. And then he'll add 110 to 4.9. He'll go this way, 4.9, and then he'll go this way, 4.9, right? And this will give you the limits. This will give you, in this example, 105.1 and 114.9. 1.96 here is a given. It's something that it's not even given. It's something that you memorize. Given is like the standard error here, or the sample mean here. It's just given to you from the question or something. But z being 1.96 is always going to be the same, right? Z being 1.96 is always the same. So I hope you understand this point, because this was all midterm stuff. Like you guys really know this from your midterm, but it's fine. I don't mind repeating it, but I just really want to make sure that you guys understand this for the time being. So this is how you make limits. Now, if he's giving you a really easy question, believe me, the easiest question he'll give you is calculate the limits, because right now we're entering a point where a lot of the concepts that he's going to ask you are theoretical. Well, what I mean by that is he'll ask you, for example, when you increase n, what happens to the confidence interval? He's not going to ask you to calculate confidence interval. He might, but he's just giving you a free point, because this is just simple stuff. The harder stuff is understanding the theory and the concepts behind the confidence interval. For example, such as, this is a very common trick that I'm sure you will see in an exam. I am absolutely sure you will see this. He will give you this trick. He will say that, for example, I'm just going to make it a true or false question. He's not going to ask you true or false, but he's going to put it as one of the choices, and it should be wrong. But here's what he'll say, for example. A confidence interval has a 95% chance of hitting the sample mean. Now, is that true or false? I want you all to answer. All right. All of you, I see 3 people saying false. False, false, 100%. Yes, okay, so Sarah, I'm really happy with your answer. I'm happy with all your answers, but Sarah, she jumped ahead and I like it. You always 100% have a 100% chance of hitting the sample mean. Because remember, this is the trick. Didn't we say that with any confidence interval, we first start by using the sample mean in the center, then we go this many points to the right, then this many points to the left. So every single confidence interval always includes the sample mean, because that's where you start from. Always. You always use the sample mean to start from whatever confidence interval. So what he's trying to trick you is he's trying to say, do you just memorize the concept or do you actually understand it? When you say you have a 100% chance of hitting the sample mean, you're 100% correct. When I tell you you have a 95% chance of hitting the sample mean, that should be incorrect. That should be 100% wrong. I sorry to say 100% like 1,000 times, but you all understand this. You always hit the sample mean because that's where you start a confidence interval from. It always has to be in the center. The true statement, again, I know you got confused, Mariam. I'll mention it again. The question deals with 2 ideas. He'll tell you, I'll show you both ideas so you understand both principles. He will tell you, here's the 2 sentences that you will confuse. One is true, one is false. This is sentence number 1. You have a 95% chance of including the population mean within any, for example, 95% confidence interval. Now that statement is true. That statement is true. With any 95% confidence interval that you get from a sample, you have a 95% chance of hitting the true population mean, because we don't know where the population mean is. We're using the confidence interval to get an estimation as to where it is. We don't know where it is. That's why we're using the confidence interval. So that statement is true. The opposite statement that's false is this one. He'll try and sneak it on you in the exam and you might pick it. This is what the statement says. You have a 95% chance of hitting the sample mean, of including the sample mean within the confidence interval. That statement is false. And the only difference between those 2 statements is at the end he says population mean or sample mean. And you might say, oh, it doesn't make a difference. No, it makes a huge difference. So wait, which was the true one? When he says population mean, that's the true one. When he says you have a 95% chance of hitting the population mean, when I say of hitting, I mean of being included in the limits, then it's true. This is true. This is a valid statement. When he says you have a 95% chance of hitting the sample mean, that's wrong. You have a 100% chance of hitting the sample mean, because the sample mean is always in the center of the confidence interval, right? Now, I don't want you to memorize. I don't want you to write in your notes that, oh, Khaled said that 95% chance population true, this one false. Don't understand the principle, because he might give you another. Okay, so let me give you another question. This is a bit trickier as well. A 90% confidence interval has a 95% chance of including the population mean. A 90% confidence interval has a 95% chance of hitting the population mean. Exactly. This is false, because you can get a 90% confidence interval, but it's only going to have a 90% chance of hitting the population mean. Only a 90%, since it's a 90% confidence interval, right? It has a 90% chance. This is how you understand it. Don't just write in your notes, oh, Khaled said this, so this is false. Don't just memorize it. Try and actually understand it. So now let me give you another example. A 90%, can you repeat this one again? I'll give you another example. A 90% confidence interval has a 90% of hitting the sample mean, of including the sample mean. Is this true or false? This is false. This is false. It should be 100%. Whenever I say sample mean, it should always be 100%, no matter what, okay? Because every single confidence interval has to include its sample mean. It always has to. The sample mean always has to be in the center, because that's the point where you go to the right and to the left. The tricky part is when he talks about the population mean. If it's a 95% confidence interval, he has a 95% chance of including the population mean. If it's a 90% confidence interval, it's a 90% chance of including the population mean. If it's you can't get a 100% confidence interval, it's impossible. But if you have a 99 is possible. A 99% confidence interval, you have a 99% chance of including the population mean. Okay. So I hope this is important. I hope this is clear to you guys. There is one more trick. This is actually okay. Look, if you get confused by this one, just ignore it. I'm mentioning this because he could bring it to you, and this is actually more of a step question than a biostats step or biostats midterm question. But he could bring it to you. This is how the question goes. It tells you if I have a 95% confidence interval versus a 90% confidence interval. Okay. Same mean, same everything, same SEM, same everything. The only difference is this one's 95%, this one's 90%. This is how the question goes. It tells you which one should be narrower. Is it the 90% or the 95%? Okay, so I'm gonna give you the answer. It's 90%. If you actually do it, it's 90%. And this should be the answer 10 times out of 10. The reason is he's not asking which one covers more data. He's just giving you which one is narrower. So if you put them side by side, this one will actually have a higher z. The 95 one will have a higher z. The 90 will have a lower z. So because of that, when you make the interval, this one won't go as far as this one. Now you might say, Khaled, hey, so if this one is narrower, why don't we use 90% confidence interval? Because remember, the standard is 5%. The standard is 5%. Journals will never accept a 90% confidence interval, right? In your step exam, they don't care what journals want. They're testing your knowledge. Do you understand that a 90% confidence interval is narrower than a 95% confidence interval? It doesn't mean it's better. It just means it's narrower, right? In fact, the 95% confidence interval is more useful, but the 90% is narrower, right? And then this is all theory. We're not going into how to calculate, this is all theory. And it's important to understand this theory, not memorize it, because that's, and yeah, you all understand why 90 is narrower, right? I just want to make sure. Just say yes or anything on the chat. Yes, okay. Yes, okay. So you all understand this. So no, okay. So I'll just quickly mention it. Look, let's say I'll do an example really quickly. So let's say the 90% confidence interval, its z is 1.6. 1.64, I think, 1.64. And the z with the 95% is 1.96. So if this number is equal, so let's say the mean is 100 here, and the mean is 100 here. Sorry, mean is 100 here. And then the SEM is, for example, 2 here, and the SEM is 2 here. You multiply this, and then plus, minus, plus, minus. The only difference between these two formulas is that this one is 95% confidence interval. This one's 90% confidence interval. This, because due to the z being lower, this number eventually will be lower, causing a smaller number being added and subtracted to 100. So the interval here will be narrower than the interval here, right? Again, you don't really, this is really a more, it's not really that advanced concept, but this is sort of a really thinking concept. Why do we multiply with 2? I just picked SEM as 2. I just picked it randomly. I just assume the SEM is 2, right? Yeah. So I hope you understood it. And yeah, that's I'm giving you tricks so that I think when you go through tricks, you start to appreciate the concept a bit more. So yeah, we talked about all of this, and now we all understand these tricks. So now let's talk about this part. This part is really confusing to a lot of people. But again, I want to go back to the midterm crash course. I'm going to ask this. I want you all to answer the way I taught you. Is it possible for someone to be 60 feet tall? 60 feet tall. Okay, yes. I agree with all of you. It is possible. So now here's the second question. Is it possible that you have a 95% confidence interval, but you do not include the population mean? Yes, it's always possible. Yes, you have a to be exact, you have a 5% chance of missing the population mean. So this is what this slide is trying to say. It's just giving you sort of a visual input as opposed to just words. So look, this is the same exact confidence interval. They're just taking different samples. Like you have, for example, like let's say you make a study, and usually you only take one sample, but just for the sake of explaining this concept, let's say you take 20 samples, right? Now these are not 20 samples, but let's imagine they are. So 19 of these samples will include the population mean. We don't know what the population mean is, but let's assume it's here. 95%, like if you take 95% of 20, you'll get 19. So 19 of these samples will have confidence intervals that hit this population mean, right? But then one it won't, and it's not because, oh, it won't, it's stubborn. No, it's not like that. This is math. 5% of the time it won't include the population mean, and this I will you will hear me say this so many times, that it's just luck. When I say it's just luck, I mean, it's when I say it's just luck, I mean it's just luck. Like, I don't know how to explain it. Like, when I say it's just luck, it means that, let's say, for example, you were studying, let's say you got really unlucky and you got this confidence interval, because remember, in studies you only use one sample. I mean, if your study design needed one sample, let's imagine your study design needed only one sample, then let's say you made one sample and you got this confidence interval. The drug doesn't work. Look at how many times, all these other samples got hit the mean, hit the actual mean. We would call all of these samples not significant, meaning that the drug you gave them, whatever, it's not doing anything. But if you happen to get unlucky and get this sample instead, you would actually think the drug works. You would say, oh, look, my confidence interval isn't touching the mean. Now we don't know where the mean is, but just for simplicity, my confidence interval isn't touching the mean. That means my drug actually works. No, there's a 5% chance that it doesn't. And this slide explains that. This slide sort of gives you a preview of the next lecture. For the time being, what's this slide trying to say? When we say you have a 95% chance of hitting the confidence interval, don't forget that there's a 5% chance that you won't. And in this case, it's this one, right? So when we take 100 samples, 5 of them will not include the true population mean. Exactly, Lean. When you take 100 samples, 5 of them will not include the population mean. And that is a nice way of thinking about it, and this is really the way you should think about it. And yeah, I really hope you understood this principle. So let's go to the next slide. Now, these are just definitions. 95% of randomly selected samples will have calculated confidence interval that contains the true population. Basically, this is everything that we already talked about. The reason he's giving two definitions is he's trying to tell you that, when you go to parties with all the biostatisticians in town, they're all going to be like, we hate these definitions. These definitions, they suck. And that happens with, like, if you go to a party with rheumatologists or hematologists or cardiologists, they will look at some definitions and they'll be like, whoever wrote this definition is an idiot, because they are so experienced that they know that these definitions are just not that good, right? If, for example, you might get a cardiologist that will, I don't know, he'll like see stenosis and he'll be like, this is fine because I'm experienced. I know that this stenosis, even though if it's 80% and the books say that it's 80%, the guy can live with medical therapy. People, this is a problem in general, not just biostats. When they become super specialized, they start to they started dislike these simple definitions and basics because they know it's not true. They know that their specialty is a lot more complicated than what they're trying to actually say. That's all this slide is trying to say. He's trying to say that, hey, I'm a biostatistician, and although we have all these stupid definitions that we don't agree on, use this definition for the time being, right? And these definitions should be good for you at the time being, right? So that's all he's trying to say. And there's nothing really to add on to here. Now, this is another example, and I think since we're still a little, I see some people asking, how do we calculate yada yada yada? I think this is good to just use this example. So we're going to do it for both. We're going to do it for 95%. We're going to do for 90%. So let's do first. Let's do 95%. So this is how you do it. You do the mean is 65, the standard deviation is 6, the n is 9, and we have z. Z here should be 1.96 for this one, 96. And then here it should be 1.6. Whoops, 1.64. God, I wish I had this. Okay, so let's do the first one. It's going to be 65, right? Plus minus, because we're going to add it once to the right and another one to the left. And then we're going to do z times SEM. So what's z here? It's going to be 1.96, right? And then it's going to be SEM. So it's 6 times 6 over radical 9, which is 3, right? And then whatever. Like if you find this, you'll get like do we need, I'll find what this is. So 65, or let's do 1.96 times. So I'm doing 1.96 and then times 2. All right, so 3.92. Now I know that this entire value is 3.92, right? I don't know if it's flipped for you on the camera, but basically that's 3.9. Is it, just for future reference, because I'm going to be doing this a lot, do you see 3.92 or is it flipped for you guys? Okay, yes, it's only flipped for me on the camera. Okay, so what I'm going to do is I'm going to do, this is a really quick way of doing it. I just do immediately plus 65 equal 68.92. So the first limit is 68 point whatever 92. Okay. Then I do minus 65, right? And then I do or actually no, you know what? We can do minus 65 again. And there you go. We got negative 61, whatever. We don't care about the negative. We just do 61.08. And those are our two confidence or limits for the 95% confidence interval. What does it mean? It means between 61.08 and 68.92, 95% of the time, we're going to hit the true population mean between those two limits. It also means that if we get another sample, and the sample, for example, was 70, I can immediately say that this sample is different from this sample immediately. I don't need to think anymore because this sample, this 70, is outside of this limit, right? So you can start comparing samples to each other by virtue of just the confidence interval. Now for the 90% confidence interval, it's the exact same. We just changed this number. It's 1.64, and I'm really having some trouble with the touchpad, so we're gonna do this really quickly. It's 65 plus minus plus minus 1.64 whatever times 2. So we're just gonna do it immediately. 1.64 times 2. Now you might be saying, well, where am I getting this 1.64 from? It's the z. If you go to the z table, but usually it's good to memorize these three ones. It's I forgot the third one, but one is for the 2.5%. That's 1.96. The other one is for the 5%, which is for the 90% confidence interval, because 5%, 5%. That's 1.64. And then there's one for the 99% confidence interval. Just find 0.5%, and that should be the one. That should be the z for the 99% confidence interval. So here, this is going to be, let me do 1.64 times 2. That's going to be 3.28. We just add it to 65. It's going to be 68.28. And actually, this is perfect because remember the tricky question I gave you earlier about, like steps will sometimes ask you this of a 90% confidence interval versus a 95% confidence interval, which one's narrower? We'll take a look. Which one is narrower? Here, everything is similar. It's just the confidence interval percentage is different. But let me find the other one. Minus 65 equals 61.72. So which one is narrower? Is it the 95% or the 90%? 0.2. Whoops. The 90%, exactly. Look, this one goes all the way to 61.08, but this one goes to 61.72. So this one's narrower. The 90% one is narrower. And that's how they find all the numbers, right? In fact, we can find here, where is it? 0. Yeah, so it's right here. So 2.5 2.575. So that's the number for your or your 99% confidence interval, 2.575. The reason I say 575 and not 2.57, sorry, can you explain these answers and how they relate to confidence interval? Yeah. So let's go back to the this. He made that up, right? What did I make up? The SEM? SEM's right here. He gave it to us, given. The 2 SEM? No, he gave it to us. See, it's 6 over 3, which is 2. Yeah, 6 divided, yeah. It's 6 divided by the square root of 9, which is 6 divided by 3, which is 2. So the SEM here is 2. He just didn't give it to us straight away. He gave us the parts of the app. Okay. So what do these confidence intervals? Can you explain the Z table again? I'll explain it. Let me just talk about what these intervals mean. So from 61.08 to 68.92, what does this mean? It means that there's a 95% chance that the true population mean will lie between these 2 points. It also means that if we have another sample, which was beyond these 2 points, we can immediately say that this sample is different from the other sample, right? And that's, again, simple stuff that we were revising. For the 90% confidence interval, it basically says that from 61.72 to 68.28, there is a 90% chance that the true population mean, 90% chance that the true population mean will lie between these 2 points. It also means, actually, no, we cannot say that if there was, for example, 60 here, then it's significant. We cannot say this because remember, significance is only linked to 5%. So again, that's why 95% is more useful than the 90% confidence interval. If we want to find the limits of a 99% confidence interval, we use Z equals 2.575 exactly. Because you see, how did I find that out? Basically, I want to find a p-value of 0.05 because this will equal, actually, wait, no, sorry, 0.005. So it's 0. Whatever, you get it, an extra 0 here. Because this will equal 0.5%. 5, whatever, you get it, 5%, 0.5%. And why did I pick 0.5%? Why didn't I pick 1%? Because you want 0.5 on this side and 0.5 on this side to give you 1%. If you take 1%, you'll get 1 and 1, which is 2, which is wrong. You get a 98% confidence interval, which is now there are some articles that use 98% confidence interval, but whatever. No, like the 3 famous ones are 90, 95, and 99. But really, the only 2 that are used are 99 and 95. But yeah, so I just memorized these 3 numbers: the 1.64, the 1.96, and the 2.575, whatever. So how did I find this out? This is the p-value. Where is it? 0.05, 1, and 0.049. So the exact 0.05 is right between these 2 values. So it's right between here. And what's between 0.07 and 0.08? It's going to be 0.075, right? 0.075, right? So it's going to be 2.575. 2.575, right? This is the Z table. This is midterm stuff. Okay. So we're almost done with this lecture, which is a kind of, let me just see what we have. Yeah. So then we just have a little talk about, and you can make sure of the numbers I got, 61.08, 68. We got the same numbers that we needed, right? And he goes over how he got the numbers here in the slide. It's the same calculation that we did on this side. So that should be all good with you. Do we need to know how to use the table, or can we just memorize? Do we need to know how to use? Yeah, look, I would suggest you know how to use the table. I think that's a much like, the reason I tell you memorize the values is because, first off, step, they might be stupid and just ask you. Second reason is you save time during the exam, which is, any minute that you save could be useful, especially if they ask you about the Pearson. Like, I had one question in my final. I finished my final in like, I think I had like a minute left. And a lot of people were complaining, me included, that we did not have enough time. And the truth is because one of the questions takes around 10 minutes. And he told us, you're going to get a question like this. So we all did the same thing. When we saw it, we just marked it and then continued the other questions. But we eventually had to do it because it's a free mark. It's just calculation, but it takes around 10 minutes to do it. So any minute that you can save not looking at the Z table is going to help you. That's why I tell you memorize the 3 values, just for saving time. But you do need to know how to read the Z table. Like, why are you guys asking me this? You had to use the Z table for your midterm. So did you already forget how to use your Z table? These are your Z values. Yes, you already forgot. Okay. All right. So Basically, if you got it, let's say you get a z. I want you all to answer this. Let's say you get a z of 1.5, 1.67. Let's say 1.67. What's the p-value? So what you do is you go to 1.6. So you follow 0.1. Okay, 1.6. Right, here it is. But we don't want just 1.6. We want 1.67. So this is 1.60, 1.61, 1.62, 1.63, 1.64, all the way to 7, 1.67. Now connect the two. Connect the two. And there you go. That's the p-value, right? And that's how you read the z-table. Sometimes he'll ask you the opposite. He'll tell you what's the z, and he'll give you the p-value. Let's say he gave you a p-value of 20%. What's the z? 20%. What's the z? Now you do the opposite. You search inside here. And to give you a little tip, as you keep going right, it goes down little. As you keep going down, it goes down by a lot. So let's go to 20%. Okay, here's 20%, 27. 24, 21. Okay, 21. Now let's go to the right for small differences. 20%. Okay, this is the closest one. So this one is going to be 0.84, right? 0.84. This is our z, right? That's how you use the z table, right? So don't forget this, because this is important. He'll probably give you the z table in your exam. You need to know how to read it, and you need to know how to get your p-value and your z-value. All right. So then yeah, this is the same example we did. Confidence interval. Yeah, so this is really important. Now he's just repeating the example here. For example, a 95% confidence interval, 95% of such calculated intervals include the population mean, yada, yada, yada. We know this. Now this is important. The mean, in other words, for example, let's say the population mean was 60, right? And your confidence interval, it was like from here to here, and your mean was like 70. How far this mean is, it represents a point estimate of the effect size. Now, what does effect size mean? Effect size means how much different the sample mean is compared to the population mean. That is the sort of idea of effect size. Now, effect size has nothing to do with significance. Nothing to do. Significance means just that the p-value is less than 0.0, less than 5%, less than 0.05. Effect size is different. Effect size, sorry, there's a little fly. Effect size means that the mean of a sample, for example, is very far from the mean of another sample, or very far from the mean of a population. It basically has to do with the mean. For example, if we had another sample that was here at 80, then we would say that this effect size is stronger than this sample. And we would say that, for example, this sample size, this sample mean has a larger effect, or a decent effect size when compared to the population mean, right? Now, usually you don't know where the population mean is, so instead we compare samples to each other as opposed to samples to the population mean. But for simplicity's sake, for explaining the concept to you, that's why I mentioned the population mean. So the position of a mean, a statistic. Okay, is it okay if you repeat this point? Of course. I'm just talking about this sentence in the bottom. He tells you that the position of the statistic, for example, the mean, within an interval, forget the interval, wherever the mean is, it gives us an idea as to how strong of a difference there is between two means. So for example, if a mean is 60 and the sample mean is also 60, we get an idea that the sample, the sample is almost the same as the population mean. But if I told you that the mean is 100 and the population mean is like 60, you would get an idea, oh wow, the sample is really different. So what did you do to the sample? Did you give them a drug? Did you give them something? So the mean gives us an idea as to where where the mean is, gives us an idea as to how strong a certain effect that we're doing on a sample is, right? So or how different a sample is from the population mean. And that's the idea from this. It should make sense to you. If I give you a sample mean of 100 and the population mean is 60, even like if you want to be perfect about it, I should also give you a standard deviation. But even without a standard deviation, you might say, oh wow, so that sample mean is really different, right? And this is called effect size. Exactly, this is called effect size. An effect size is completely different from significance, right? And we'll talk about this right now. So hold your horses. We'll talk about this more. Now, what's the usefulness of the confidence interval? It gives us precision as to where the population mean is, yada, yada, yada. So the width of interval is a measure of the precision for the population mean. In other words, if we know that the confidence interval is from, for example, 100 to 102, then we are really precise that the population mean is somewhere in between that, which is really useful, because we don't really know where the population mean is sometimes. Now, conversely, a narrow interval suggests a high precision. High precision, you get it by increasing your sample size. This is all the same things. It's also very easy to understand. Like I told you, if we most articles, they just put the confidence intervals, and then it becomes very obvious whether something is significant or not just by looking at the confidence interval. And this is something that even at the med student level can understand. If the confidence interval is from here, for example, here to here, and then the mean is like here, you can immediately tell. Whoops! You can immediately tell that this population mean, or this, sorry, sample or whatever, it's very different, or it's very significant when compared to this confidence interval because it's outside the limits. So this is why they like using confidence interval, because it gives you an idea. The problem is that you only know that it's significant. You do not know how significant it is. In other words, this sample mean that I just said it's significant, all I know about it is that the p-value is less than 5%. I don't know what the exact p-value is. I don't know if the p-value is 0.02 or 0.03. I don't know. I just know it's significant. And that's a very important idea with confidence intervals. He might give you a question. With a confidence interval, we're able to find out the exact p-value. This is incorrect. You can never find out the exact p-value using only a confidence interval. You have to just appreciate that you can tell using a confidence interval whether the p-value is less than 5% or more than 5%. The only way you can do that is you just look at it. You just say, oh, the mean that I'm interested in is outside this limit. That means it's significant. Can you repeat this point again? I got lost. Okay. So what I'm talking about right now is this slide. So he's saying that a confidence interval does not give you a p-value. Now, I'm kind of jumping ahead to hypothesis testing, but remember in the midterm, oh, that was like a really long time ago. Remember in the midterm, I was talking about 5% and the tea lady. Do you remember any of that, guys? Do you just say yes, no, anything? Yes. Okay. So I'll just no. Okay. So I'll just give a nice little recap as to what tea lady was. Okay. So tea lady is the tea story, and the tea lady story is the foundation of biostats and why we use 5%, right? It was in the previous lecture to this. It was at the end of it. And basically the idea is that a lady was saying, hey, if you bring me 6 cups, it's not actually 6 cups, it's like 8 cups, but just to make the math simple, it's 6 cups. If you bring me 6 cups, and if you put, for example, the sugar, then the tea, or the tea, then the sugar, or the milk and the tea, whatever. Point is, I'll be able to tell the difference. So then one of the biostatisticians said, okay, I'll see if you can really do it. So what he proposed is that 3 of the cups will have sugar first, and 3 of the cups will have tea first. And he calculated what's the chance that she'll get it by luck. And the chance she'll get it by luck was 5%, 1 out of 20. So he said, okay, 5% is very low. It's very, very low. So if she managed to get it, I'm going to believe her. And I'm going to believe that she really can do it, even though it is slightly possible that she got lucky, right? So, and then, she did it. And then Robert Fisher, being a believer of numbers, believed her that, hey, you had a very small chance of getting it by luck, so I'll believe you got it. This is where the 5% idea was born. So now studies, they use a 5% significance level, which means that if your sample, the only way you could have gotten that sample through luck was 5% or less, then you start ruling out the idea that it could have been by luck. You start saying, no, my drug works. My drug works. What? You're telling me I only had a 5% chance of getting my sample? That's very lucky. It's probably that the drug works. That's why my sample was really different. That's why my sample was outside the confidence interval. That's why my sample is really far away from this interval and not inside this interval. That's the idea of 5%. Basically, if it was 10%, I know all of you are saying, but 10% is also low. I know it's low, but the cutoff is 5%. If it was 6%, you would say, no, I got it by luck. I got it by luck. The drug doesn't work. But if your sample, the chance of getting it by luck was only 5% or less, you would say, nope, no chance it's luck. I say no chance it's luck, but there's a 5% chance it's luck. But the idea is that, nope, it's very, very unlikely for it to be by luck. I think the drug works. I think the drug works. That's the idea, right? And we'll talk more about this. I know this isn't a very easy concept to understand, but this is the basis of the next lecture. So if you didn't get it now, It's fine. You can get it in the next lecture, where this concept is a lot, we can really flesh out all the concepts with this idea. For here, well, the only thing you need to know is that with a confidence interval, usually, what we do is we find the exact p-value. For example, p-value equals whatever, like 2.34%. Okay. So look, this is a really like we go to the z table, we find the exact p-value, yada yada yada, blah blah blah. With a confidence interval, the only thing you can know is that the p-value was less than 5% or more than 5%. You can't know anything else. So he might give you a theoretical question. He tells you the confidence interval can do which of the following, blah, 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 and then choice C is like a p-value. It can give you an exact p-value. This choice is also wrong. You immediately get rid of it. A confidence interval does not give you an exact p-value. It only tells you, is your sample less than 5% or is it more than 5%? Because that's all you can get from this. If your sample was here, outside the confidence interval, the only thing you know is that this is less than 5%. You don't know if this is 2 or 3. In fact, I'll make it even. This is going to sound confusing, but I'll explain it in a few slides. Let's say this was our interval, and let's say you got a sample here. Is this significant? Is this p-value less than 5%? This one, compared to this interval. You all say yes. Now, if here's the shocking part. I know you're all going to say, no, this is impossible. No, no, no. If you get a sample here, beyond, even further away from this one, this and this might have the exact same p-value, despite this one even being further away from it. I know you're all like, no, this is impossible. No, this one's clearly further. This one should have a lower p-value. No, this thinking is wrong. This thinking is absolutely wrong, and you'll see why in just a few slides. And it could be more like here. This p-value could be more, could be less, but the idea is it's not always less. It's not always less. Okay, it could be more, could be less, could be equal. You never know. But the idea is that just because it's further doesn't mean that the p-value is less. The only thing that the confidence interval, using this technique where if it's outside it's significant, the only thing you can do is figuring out whether the p-value is less than 5% or more than 5%. Okay, and you'll see a beautiful example of this coming up soon. But you all understand this, right? You all understand this entire slide where it's just trying to tell you that by using a confidence interval, you do not get an exact p-value. This is incredibly important, okay? Now, can I get some yeses just so that we can see if everyone understands? Okay. When I say like, can I see some yeses? I'm only interested if someone says no. So I'm not seeing any no's. Okay. So now this is important. This is really important. Remember when you remember this exact example? I was telling you that just because this is, for example, closer than this, then that doesn't mean that this p-value is more or less. But one thing, absolutely for sure, this mean has a stronger effect size than this mean. That's the important part. People think, oh no, the p-value here is less. No. That's p-value is not linked to how far the mean is. P-value is only linked to the limits. If it's beyond the limits, khalas, p-value less than 5%, you can just understand that part. P-value has nothing to do with the relationship as you go outside the limits. What does have a relationship is the effect size. The further away the mean is, the stronger the effect size. Now, I know what you're thinking. Is there any link between p-value and effect size? Zero. No link. These are two completely different concepts. Effect size has to do with how far the means are. If a mean is further, it has a stronger effect size. P-value simply has to do with the percentage of getting a specific result. In this case, if you're beyond the limits, you know that it's significant. You know that the p-value is less than 5%, but you don't know what the p-value is. People sometimes, they try and link these two concepts together. There is no link, no relationship, nothing to do with these two. They both describe completely different things, okay? So this entire slide is really big, but we just talked about it, and he gives you some examples. We're not going to, it's sometimes called the magnitude of effect. No link between which two? P-value and effect size. There's no link between these two. Absolutely no link, okay? And you'll see the example I'm going to show. So sometimes it's called the magnitude of effect, the effect size, the size of effect. This is concerned with how big the effect is, how further away a mean is from another mean, or the difference can be standardized, has several different notations like Cohen's d, which is difference in means divided by. He's not going to ask you how to calculate. Odds ratio is another way you can calculate. Like these are just nomenclatures. And sometimes you can guess, you can sort of get an idea or estimate effect size by doing, for example, a pilot study. A pilot study is like a test study. Like, for example, you plan on doing a study with 2,000 people. Maybe you're scared you might run into some problems. So what you do is you start with like 50 people just to see, hey, what problems are there? Is the effect size good? Is the power good? Yeah, we'll talk about what power is yet later on. This is the idea. Sometimes you can just use the effect size. You can estimate the effect size using a pilot study. You can use it by doing pre-studies, blah, blah, blah. So sometimes pharmaceutical companies can set a minimum for how much they want an effect to be done. For example, let's say you make a medication. It is statistically significant that it will drop blood pressure by 1 millimeter mercury. No one is going to care about that, because even though it's statistically significant and you can make it statistically significant, even if it's just 1 millimeter mercury away from it, it doesn't matter, because no one's going to pay for a medication that's only going to reduce it by 1 millimeter mercury. Okay, you don't get effect size. Effect size, you'll get it. Look, let's say this is the population, and whatever, we found the confidence interval, blah, 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 blah. Let's just say this is a sample, okay? And from the sample, we got a confidence interval from this to this, okay? And this is the mean. And let's say this is blood pressure. Let's say this is 120. The mean is 120. Systolic blood pressure only, okay? Now, if you got a medication that increased your blood pressure to 140, now it is, here's the question. Is it significant or not significant? Is this mean significant or not significant? The limits are here. This is the first limit. This is the second limit. Okay, you all agree that it's significant. Okay, now, does this have an effect size? Let's say companies only care if the medication will raise blood pressure by 10 millimeter mercury. So, for example, if you go from 120 to 130, let's say this was, for example, here 130, then they would say, okay, that has a good effect size. So yeah, you all agree it has an effect size, right? 140, it raised it by 20. Companies will pay for that. What if you found another medication which raised it to 160? Does 160 have a larger effect size than 140? Yes. Notice, I'm not even, when we're talking about effect size, I'm not even talking about confidence intervals. I'm just talking about means. So the further means are, the larger the effect size, the stronger the effect size. Now, sometimes, this is how people cheat, okay, in biostats. Sometimes they can make a limit so small by putting in like 1 million people in the study. So for example, the limits would be here and here, and like the graph would be like this. Right? This is the distribution, and the limit is here and here. Yeah, we cannot say 160 is more significant than 140. This is wrong. You cannot even say it's less significant. You can't say it's more significant. It could go either way. You don't know. You only know that it's significant. So this is, for example, 120. Let's say this is 120. So the guy, he got like 1 million in his study, right? So his confidence interval is so small. It's so small. So then his mean is 123. So there you go. He's like thinking, oh, I'm amazing. I got a statistically significant study. I have proved through statistical significance that, and through numbers, that my medication can increase blood pressure by 3 millimeter mercury. Does this have an effect size? Effect size. I'm not, look, forget. No one answer. Wait. No one answer. Stop. These are the limits. Let's say, for example, 121 and 119, okay? We only care, okay? We set an effect size. We set the minimum for clinical importance. We set it at 130, meaning that if a medication, raises blood pressure by more than 10, in other words, raises it beyond 130, then we say it has an effect size. And as you go further, we say it has an even stronger effect size. So look, is 123 significant? Here are the limits. Take your time. Here are the limits. Okay, yes. So this is significant because, he cheated. He got like 1 million people in a study. Of course, the confidence interval will be extremely narrow. And you'll see this, like, if you actually work with people and researchers, sometimes they will try and do this trick. But good journals will never accept this trick because they will say, we care about an effect size bigger than 10. Here, your effect size is only 3 millimeter mercury. Why do we care about this? Limits are 120, no, limits here, for example, are 121 and 119, and the mean is 120. The guy's sample mean is 123, okay? Are you all with me? And the effect where we say it has an effect size, if it's beyond 10 points, whoops, if it's beyond 10 points, how the hell do you get this way? Oh, if it's beyond 10 points, then we say it has an effect size, okay? So here in this case, it's significant because it's beyond the limits of 121 and 119. It's beyond this limit, so it's significant. But it has no effect size. It only changes blood pressure by 3 millimeter mercury. Who cares? Who cares? Like, what's this gonna do? It's not gonna do anything. You get it? So this is why I'm telling you that effect size has nothing to do with significance. It has absolutely nothing to do with it. It's just, people think that, oh, if my study is significant, I'm big, I'm strong, I can now publish in Lancet, and I have an amazing study. No, you need to make sure you have an effect size. There are way more things that are important as opposed to just, getting a p-value. But unfortunately, people think that, oh, it's just p-value. Then they get, upset that they don't get published in Lancet, which is just, it puts the cherry on the cake, to be honest. Point is, you all understand now effect size, right? Effect size simply deals with the mean. Is the mean going further and further away from the actual, population mean or sample mean, whatever? If it's going further and further away, either to the right or to the left, we say that the effect size is getting stronger and stronger, right? It deals with the means. That's effect size. And sometimes you can estimate it. He might bring you a theoretical question saying, which of the following can be used to, estimate it. Just memorize them. You can use a pilot study. You can use a minimum of clinical importance. This is usually dictated by pharmaceutical companies, or, for example, certain guidelines, like certain guidelines. Sometimes there are doctors sitting in Mayo Clinic and they're like, okay, we're going to make a new guideline. Basically, we're only going to take medications that are going to decrease blood pressure by 20 millimeter mercury. They make a guideline. They set up the clinical importance, and then people make the medications that will decrease, and they set this effect size as their goal. Or you can use collected data, which is of course, like after you collect the data, you find the effect size, which is like hilarious, kind of. He sometimes puts obvious things in his lectures, which you'll see in the lecture comparison of means. So you understand the effect size. Now, here's what I'm saying is, p-value doesn't correlate, or there's no relationship between p-value and effect size. Sometimes your p-value is small, so it's significant, and the effect size is good. This is excellent. This is a great study. Okay, you found a good effect size. It's statistically significant. You're gonna make a difference. Go publish in Lancet or wherever you want. Perfect. This is amazing. We want this. The problem is sometimes when you have a small p-value, it's significant, but there's no effect size, which is the example we talked about here. Here, they make the mistake of thinking that statistical significance, in other words, oh, my drug is statistically significant, but your effect size is just, it's nowhere to be found. It's just 3 millimeter mercury. Who cares? Your effect size is small, so you make the mistake of thinking that just because it's statistically significant, that it's going to help you, for example, clinically or something. It's not going to help you. It's not going to help you. It's terrible. And this, I'll just forget this for now. Forget this for now. We're gonna talk about this later. Okay, forget about this. This is way too confusing to ask to question you about it now. Now, sometimes the p-value is large, meaning it's not significant, but your effect size is strong. Right? You might be saying, well, how come? If your effect size is strong, that means your mean should be really far. How come it's not significant? Usually the problem here is that he did not take enough people in his sample. In other words, his confidence interval is so wide. Remember that other guy was cheating by making his confidence interval so small. Here the example is opposite. He has a drug that really pushes for example, it changes blood pressure by like 40 millimeter. It's really good. But he only tested it on 10 people. So the confidence interval is very wide. It hits the mean, and you think that there's no statistical significance. Here, the only way to remedy this, to fix this, is by repeating the study, but increasing your sample size. And sometimes the effect size is small, so the drug isn't doing it really that much, and the p-value is large, so it's not significant. Here, there's no problem, just... okay, I almost made a mistake. I was going to say just cancel the study. Sometimes proving, and you might be surprised by this, but I'll show you it when we talk about ANOVA. Sometimes proving that two things are similar is actually a good thing. Sometimes proving that there's no effect size and that there's a large p-value, that's good. For example, and you'll see this example in ANOVA, if you can prove that a placebo is the same as conventional therapy, like giving dopamine or stuff for Parkinson's disease patients, that's an incredible study, despite there being zero effect size or a small effect size and a large p-value, because you just proved that these two things are similar. They're not far away from each other. You just proved that a placebo is the same as actual treatment. So you don't need to, if someone comes in and they want to get dopamine, you can just tell them, hey, you're not going to tell them it's a placebo, but like, you're just going to tell them, oh, here's some dopamine. You just give them a placebo, you give him sugar or something, and you tell him it's going to taste very sugary, take it with some food or something. And he might believe that that's, actually medication, and he might benefit from it. So, this is another mistake that I almost made, where if the effect size is small and you don't get a statistical significance, people think, oh, the study failed or something. No, sometimes proving that two things are similar could actually be of importance. It just depends on what the study is aiming for, and we'll see this more in ANOVA. So it's effective in proving something doesn't work. Yeah. If the effect size is small, it shows us that this whatever this sample was taking is similar to the population that, for example, maybe wasn't taking anything. So, for example, if I have if I take two people taking dopamine and people taking placebo, and I prove that these two people are the same. In other words, the effect size is really small, their means are stacked on top of each other, their confidence intervals are hitting each other, everything is like overlapping each other. I just proved that placebo is the same as conventional treatment, which you know, uh, people make this mistake of scrapping the study. Oh, this is terrible. Our study failed. There's no statistical significance. No, this study did a remarkable thing. It basically, freed up all the patients who are paying so much for dopamine for Parkinson treatment. Instead, you can just give them placebo, which costs, little to nothing. It's just sugar tablets or something. So again, this he might give you these. This is an exam question, telling you, for example, a study had a large effect size and a large p-value. What is this? And he gives you, for example, it's not a problem or whatever, and he says it's a failure to detect scientifically important effect. So commit these to memory and understand them. I didn't get small effect size. Where will it be located on the interval? Okay, first off, effect size has nothing to do with intervals. Effect size has to do with means. For example, let's say this is the interval, whatever, but the mean is right here in the center. Let's say we got another mean that was right here. This means the effect size is so small. Look at how they're almost stacked right next to each other, right? And let's say we only consider it being, important if it's more than 10, beyond this number. Whoops, beyond this number. So here in this point, usually I get your question, and who dictates that the effect size is large or small? Usually it's done by companies or guidelines. They tell you that, hey, we only care if you make a medication that goes beyond, for example, 10 millimeter mercury or whatever, right? So uh, it depends, and he probably will he'll mention this in the question. But let's take some more examples. So here he gives you a whole like text of slides there. Um, on the basis of p-value, we make a decision on whether to not reject the null hypothesis. I'll see your question in just a second. So this is a next lecture. Let's just leave this for the next lecture. Basically, if the p-value was more than 5%, what we do is we say we accept the null hypothesis. But if the p-value is less than 5%, we say that the p-value, we reject the null hypothesis. So we'll talk more about this in the next lecture, what the null hypothesis is and so on and so forth. Um, so he tells you sometimes this is subject to error. This is again part of the second lecture. We'll talk about this. The use of confidence intervals helps determine whether this type of error has been made. Yada yada. This is all he's priming you up for the next lecture. So let's just ignore this for now. They also help decide whether the magnitude of effect we have observed is of scientific interest. So this is where p-values and confidence intervals can help us. Now he doesn't mention this for the last point. He says that, oh, we can use confidence intervals to help us with the determining whether there's an effect size or not. Actually, I would argue that this sentence is slightly wrong, because he will go against his words in the following slide. He's not going to use the confidence interval per se. he's going to use the mean of that interval. He doesn't mention this, but this is what he's trying to say. So before I go on more, let me just take some questions. Wait, but if the effect size was small and the p-value is large, that makes it not significant in the first place. If the effect size was small and the p-value is large. Yeah, how does that help? See, now you're falling into my trap, which I almost fell into. When the p-value is large, right, and the effect size is small, like let's say for example here, I want a blank slide. Okay, let's say this is the sample, and they, for example, scored like you gave them uh, dopamine. These are Parkinson's disease patients, and you gave them dopamine, and then they eventually took a questionnaire that told them how better how better they're feeling, and how they can move, and how they can do everything, and they said, their mean ended up being 7, right? And then you made a confidence interval for that, and you found, for example, 9 and 5, right? Now, if we take the same sample, but for, or not the same people, but like a different sample, but we gave them placebo instead. So this is the dopamine group. This is the placebo group. What ends up happening is they also give 7, and then you find the confidence interval. Let's say, for example, it was different. It was let's say it was 4, and let's say it was 10. Now here in this example, their means are right on top of each other. So we can agree that the effect size is minimal, very minimal. In fact, it's 0 technically. And if you do the confidence intervals, this confidence interval, 10 and 4, it includes this mean, right? So we can already just say that the p-value is more than 5%, because it's not significant. This confidence interval includes 7. And we can do it vice versa. This confidence interval, 5 and 9, includes this 7. So we're sure that the p-value is large, and that the effect size is small. So any other person would just scrap the study. He'd say, oh, we failed, we didn't find an effect, we didn't blah, 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 blah. No, here you proved one very important thing. Because the p-value is large and because the effect size is small, you prove that these two, samples are the same. So you prove that whether you're on dopamine or placebo, there's no difference. And that is important. That is very important. That is actually, you saved so much money from all the patients that are going to buy dopamine. All the companies. Oh yeah, that makes sense. Perfect. Basically all the companies that make dopamine, they're going to start to hate you because you just, you made them go bankrupt. Now, obviously, dopamine is used for other things other than just Parkinson, but the idea still stands that it's not just about having an effect size or having significance. Sometimes not having significance is actually pretty good. It's actually pretty good. So I hope that this makes sense so far. Now we're gonna practice our knowledge, okay? So this is, and I want all of you to answer. This is the population mean, okay? Now let's say the population mean was 100 in this case, okay? Sometimes, instead of saying 100, and this is very common, this is common, practice in articles and everything. Instead of saying the population mean is 100, we just compare it to a null value. So what that means is that instead of, for example, this being, let's say, 117, we would say that this 100 is 0, and everything after 0 is, for example, 2, 4, 6. So this would be 7, as opposed to being 107, right? It's the same exact thing. When you go from, are you all with me? Like, instead of saying 100 is your population mean, and then the sample mean is 107, it's just the opposite. We say 0, and then that one's 7. Right? And this is just for convention. This is just um, for the ease of understanding that we all need to go to 0 as opposed to 100, for example. Wait, where's the population mean? So this is you see, I don't know why this slide is different for us. This slide he used horizontal. Here the mean is actually vertical. So the mean here is 100, and it's called the null value. And as you keep going up, the mean is increasing, okay? I don't know why he did it like this. In fact, yeah, this is the slide we had when I was in second year. So here is the mean. See, by convention, we wouldn't say this is 110. We would report this in the article as 0. Now, what's the importance of this? It's because this will kind of confuse some of you, but like we need to talk about it because he mentions it again in the following lectures. we don't say 110 here. We say 0 because then if every single study does that, no one needs to talk about it anymore. Because we can just all assume that it's 0. 0 is the where we're starting from. So any confidence interval, the number we're looking for is 0. So for example, if confidence interval, if here it was from, for example, 20, whoops, 20, and this is like 40, right? Ideally, this is 120 and this is 140, but what ends up happening in the article is they scrap this number and they say it's 0. They say it's a null value, it's 0. And they say that this number, instead of being 120 is 140, it's 20 and 40. They tell you the confidence interval is 20 and 40. When you hear that, this is what you should think. This is important for practice and for the future lectures. You should say, oh, is 20 and 40 including 0? If it's not including 0, it's significant. Do you all understand it? Why isn't 0 from 100? Because because in this example, okay, I'm sorry. This is actually different. The 0 is 100. No, I agree with you. The 0 is 100. I just made it here just to explain the example, but to be perfect, the 0 starts from here. Could you repeat, please? Okay. And when you go to a study, when you go to read, I wish I got you guys a study so you can like see it. But look, when you go to any study, it's going to tell you the confidence interval is 2 to, for example, 7. But it won't tell you. It won't tell you what the population mean. It won't tell you, and it won't tell you what the sample mean. It won't tell you anything. It'll just tell you the confidence interval is 2 to 7. Now, why do they do this? Because they assume, every study assumes that if they did not mention the population mean, the sample mean, blah, 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 they assume that it's 0. Okay, so you will immediately look, is 0 included between 2 and 7? Is 0 included between 2 and 7? No. So that means that means you immediately understand in your mind it's significant. They don't have to tell you they don't write in the article. They just say, oh, it's statistically significant, blah, 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 blah. They give you the confidence interval, they give you the p-value. This is how they report the study. But they don't ever tell you that, please compare it to 0 to be sure. No one writes like that. You just think of it when you're actually seeing the study. Now, the problem here is that he's giving you a mean of 100. Sometimes he will not give you a mean of 100. He'll tell you null value. This is why I'm explaining this to you, because here there's two ways you can say null value. You can say 100, right? 100, and then you can, oh my god, and then you can say, for example, this is 112, 114, 116, 117, blah, blah. Or you can do the opposite, which is the exact same. You just say that this is the null value, this is 0, and then this is 2, 4, 6, 8. Yeah, but this null value and then 2, 4, 6, 8. This is the convention. This is the general. This is by tradition is always how we do it. Null value is always a mean of 100. No. In this case, their mean is 100. Another study might have a mean of 120. Another study might have a mean of 5. Another study might have a mean of 70. Another study might have a mean of 20. But by convention, none of them report that mean. They instead always assume the mean is 0, and then whatever increases there, yeah. So the null value is the mean. Yeah. So 0 is the mean. 0 is the mean, unless stated otherwise. Again, I'm just mentioning this because it's kind of confusing seeing here null value, and then you see here 100. 100 here is the null value, and you can. And guys, listen, guys, relax. Okay, it doesn't make a difference if here it's 100, then 110, 120, 130, or if I say 0, then 10, then 20, then does this make a difference? Does this make a difference? I'm sorry if I'm getting a little. No, it doesn't make a difference. So by convention, every single study, usually almost all studies, they adopt this approach of using 0 as opposed to using their mean. Because if we all use 0, we're all going to look similar, and we're all going to be able to standardize the way articles look like, right? So 0 or 100, right? So the mean is 0. So the mean is 0, or for example, yeah, so the mean here, technically, it could be 0, but here, for this example, it's 100, okay? So let's start with trying to show you how to understand confidence interval, okay? So look, I'm going to do it once, then I want all of you to sort of, understand with me. So here, look, this is how you read articles. Now, they're not going to give you all, or they could give you all of these, but like it depends on how many samples they have. They could have, for example, just this one, or they could have all 5 different samples, so on and so forth. Now, this is the null value. But this mark right here, anything after it, they consider that of clinical importance. In other words, beyond this line, they consider that the effect size is good. And as you keep going higher, it's getting even better. Okay. So now what is A? Well, A, first off, is not touching this mean. It's not touching it, right? Remember, we're going up and down. A is not touching it, right? Whoops. A is not touching it. That means that A is statistically significant. We can all agree on that, right? If it was touching this mean, we would say that it is not statistically significant. That is, we all can understand this, right? Now, we would also say that since the mean, okay, is beyond this line, we can also say that the effect size is very, very good. All right? You're all with me on this. Let's do the second one. The second one is slightly a bit more complicated. Now, we can still agree that it's significant because it's not touching the mean. However, the effect size is a little bit trickier. The mean does go beyond the effect size, but it has some values that are under the effect size. Usually what articles would tell this person, they would tell them, hey, repeat your study and gather more data, get a higher sample size, because it will get narrower and eventually it might become just like A, right? Right? But this, it looks like if he collects data, he'll probably be able to become like A. But we can't say that it's important full on, right? You can't say it's important, yeah, because there could be some values here, right? Now C, let's take C. C is not touching the mean, so we can still say it's significant, but it's not important because not only is the mean or less than what we deemed it to be important, it's the values that are within it are also important. If this was maybe creeping up to here, we would give him the same advice as B. We would tell him collect more data. Either you go and become like C, or you become like become like C or become like A, right? So, but if he's only here to here, then that means that it's not important. Hey, you got statistical significance. Okay, the drug works, but we don't care about it. It's not gonna make any changes. So B has a good effect size, but it could get better. B, the best way you would mention this is B could have a good effect size, but just to be sure, collect more data, right? With C, what determines the importance line? Usually, I told you, like people sitting in Mayo Clinic, the big doctors and everything in Rochester and all that, they make the guidelines. Like literally one day they're like, this is a terrible guideline. Let's change it. And they'll say, we're only going to give drugs that are 20 millimeter mercury or blah, 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 that are going to decrease yada, yada, yada. Okay? How do you get the line of importance? Are these the values that lie outside the 95% confidence? No. Look, this is the confidence interval, okay? When we say significance or not significance, the only thing that we care about is this value, the mean. The importance, so C is the cheating thing. Yeah, so C is the cheating thing. When we talk about importance or not importance, it's usually determined by pharmaceutical companies, guidelines, so on and so forth. So what is D? D is a really funny one. It's not significant, and it's most likely not important, because if he collects data, this will become narrower to around here, and it'll become narrower to around here. So D is, I'll tell you, D is like C, but he collected very little data, right? Which is kind of funny. If he collects more data, he will end up looking like C. Let's take yeah, we're almost done. Let's just 2 minutes. Let's just, we're very close to finishing. We're going to take a break right now. So D will look like C if you take more data, but look, D is crossing this line, so it's not significant. At the current moment, it's not significant. And it's most likely not important, because even though it has some values crossing here, the mean is here. So if he collects more data, most likely it will become narrower and narrower, and it will end up falling within this region, which means that it will end up looking like C, which means that it's not really that important. We can just ignore it. And this, it's both. It's not significant and it's not important. And someone mentioned that, oh, hey, this could be an example like the placebo and conventional therapy. Yeah, it could be an example of if they were the same, right? But in the ANOVA lecture, I think he gives an example where placebo and this are different. But I just give the example. Imagine they were the same. It's pretty good. So yeah, this is that. Now I just will give a quick example about this. Remember when I was saying, hey, look, this is significant. And this is significant, right? We all agree on this, right? Can you all just say yes? Forget this line. This line is about the importance. Forget this line. Right now, I'm just talking about significance. Now, remember when I said, let me erase everything. Remember when I said that just because this is farther away, the p-value could be like, you would think, oh, hey, look, this is further away than this one. So that means that this p-value is way less than this p-value. It's more significant. That is completely a wrong idea. Never go through this route, because look, I'll prove to you right now. Now, if they have the same z, you can agree with me that they'll have the same p-value, right? So for example, didn't we say that z will always give you a p-value? So if this z and this z are the same, then we can all agree that they will have the same p-value, right? If this z is like 5 and his z is like 5, they have to have the same p-value, because you'll go to the same z table, you'll get the same p-value every single time, right? So look, count with me. What was z? Z was the number of standard deviations. So how many standard deviations is from here to here? How many is this? Remember, this is a 95% confidence interval. How many z's is this? 2. It's 2, not 1. 1 is half of this. Half. Remember, we're going 2 standard deviations. So right now, going to this point, we have 2 standard deviations. If we go the same amount, we have 4 standard deviations. If we go the same amount, we have 6 standard deviations. Wait, how? Because remember, when we take a confidence, you didn't understand this? Okay, look, wait, calm down. I don't know why you guys don't understand this. This is midterm stuff. When we take a confidence interval, what do? We do, for example, 105. This is the mean, plus minus, and then what's the z? What's the z? What z do you put here? What z do you put here? Come on, you guys need to answer this. 1.96. So it shouldn't surprise you that when I tell you from here to here, how many z's is this? It's 1.96, but I say it's 2 because that's very close, right? So this z is 2 standard deviations, right? Because z is the number of standard deviations. So we can all agree that this is 2 standard deviations. Go another 2 standard deviations. This is another 2. Let's go another 2. This is 2. So 2 is z. Yeah, 2 z. Look, guys. Z equals 1. I don't know why you guys are finding this very difficult. This is literally midterm concepts. So if the z is 1.96, I'm just telling you that. So from here to here, the z is 1.96, which is 2. Let's just make it simple and say it's 2. So if we go another 2 z's, that will be 4. If we go another 2, that will be 6. And hey, we reach the population mean. So from this point till the population mean, our total z is 6. Let's do the same thing here. From here to here, that's going to be 2 z's. From here to here, that's going to be another 2. And then from here to here, that's going to be another 2. So that's going to be also 6. So the z, when you look at it from here to this point, we have 6 standard deviations. And from here to here, we have 6 standard deviations. So the p-value for this or this, believe it or not, they're the exact same. And he goes on to tell you this. Look, the midpoint of each is 6 standard errors above 100. That is completely true if you calculate it. The z values and p values are identical. And you'd never think this. Look, the mistake is you think, oh, hey, this is low, this is high. So the p-value here is stronger, it's less. This is wrong. This is wrong thinking. It could be higher, could be lower. Has no relationship with how far it is. What we can say for 100% sure is that this effect size is stronger than this effect size. Then they give another few examples. We talked about these. This guy is not significant, whatever, we don't care about him. And this guy should collect more data because, when you collect more data, we talked about all of this. When you collect more data, you raise your power. And what's the problem with these confidence intervals that cover all of this? Is that their power is low. Now, what is power? We'll talk about it in the next lecture. But basically, the idea is that when you collect more data, you will become narrow, right? Now, you won't be perfectly narrow in the middle because as you collect more data, your mean might shift more to the right, might shift more to the left. You never know. But the idea is that when you collect more data, you might end up looking something like this, or possibly something like this. So if you get a confidence interval like this, the one thing that you need to suggest to these people is that they need to collect more data, right? This is the idea from this. So for example, here the mean is 100 and the importance is 110. well, what do you advise this person? Collect more data, because you're covering way too much data. When you collect enough data, he eventually has to go either to this side or to this side, and from there you make a decision. Similar to how when we were talking about these. Remember, let me erase the ink so you can look clearly. Well, what would you advise this person? Take more. You wouldn't advise him take more data, but like he would end up looking like C. What would you advise this person? Take more data. If someone would had like a mean here, and his confidence interval is like this, what would you advise this person? Take more data. Why? Because the power is too low. What is power? We'll talk about it in the next lecture. But yeah, this is the entire lecture, and right now we can go prepare. Let's pray, and then we'll come back. I'll come back a little early. We'll start at 5:30. Okay, yeah, we'll start at 5:30. If you pray and come back, I can answer some questions. Okay, so I'll pray and come back. Okay, so yeah. Do you mean this one? Yes. Okay. So look, uh, this slide. First off, this and this are both significant because they're both not touching this mean of 100, which we explained. They have different effect sizes. Now, this is the effect size that we care. Anything beyond this effect size, we say, hey, it has a good effect size. Okay. So what I'm just trying to explain from this is he's really just trying to show you how p-value does not, like, just because this has a stronger effect size, this one has a stronger effect size, it doesn't mean that this has a better p-value, like a smaller p-value or something like that, or it's more significant. It has no relationship. And the way to prove that is if we find how many z's this one is from the population mean, and how many z's this one is from the population mean, and they're equal, they of course have to have the same p-value, right? And if this had less z's, then basically it would be less significant than this. And if this had less z's, it would be less significant. So what I'm just trying to say is that it has no link. Based on just the position itself, it has no link. You're supposed to sort of calculate it using z's. So both are important. No, this one is significant and important. This one's only significant, but it's not important, because if I remove all of this again, notice how this doesn't touch the mean, but it doesn't go past this line, which says that it's important. Look, difference greater than 10 units is of practical importance. They're saying that if this is the mean and you go beyond 10 points, so you go beyond 110, that means that it's important. Now this, it satisfies it. Blue line is for effect size. Yes, blue line is for effect size. So this line is for effect size. Going beyond this. This one, although it doesn't touch the mean, so it's significant, it doesn't go past. This effect size is very small, and we define that by here. Usually it should be given, right? What conclusion do we make about D in the next slide? Yeah, so I really went fast on all these. I want everyone to come back because I'll explain them. Yeah, so here we're not thinking about limits, only mean. For effect size, we're saying, oh, hey, look, this mean is here and this mean is here, right? So basically we say that this effect size is stronger, right? Sometimes when the interval is like this, it sort of is a tough one to hit, because there are some values below 110. So what we say is, hey, collect more data. You'll eventually be like this graph, all right? It'll be like this graph. So yeah, you pretty much, I hope you understood this. So since some of you are back, I'll just quickly test you. This one, is it significant or not? It's not touching this mean. So you say, yes, it is significant. Is this one significant? Yes. Can you say that this one is more significant than this one, or that this one is more significant than this one just by looking at them? No, you can't. You have to actually calculate the standard deviations and see which one has more z's. In this case, if you check the standard deviations, this one will be 6 away from the mean, and this will be 6 away from the mean as well. They have the same z, so in this case, we got really lucky. Both are exactly equal. Sometimes one will be less than another, but the point is you can't just use the location of the mean to figure out whether it's more significant or less significant. You can't. Now here's, is this important? Is this important? No, right? It's not important because it doesn't cross this line. It might look something like this, right? You could have one that looks like this. Here you tell him, hey, since you have some values that are important, repeat the study, collect more data. Because once you repeat the study and collect more data, it will eventually either look like this, or the mean might shift and you get very lucky, you get all the points here, and then it gets shifted and becomes looking like this, right? So whenever you are sort of skeptical, you can pretty much use not only the mean but also the interval to tell the person whether to collect more data or not. In this case, if he looked like this, the mean would look, my cat is really the mean would, you tell this person it is likely that this person does not have oh my god, I'm really sorry, I'm getting really confused right now because too many things are happening. Let me repeat this. This person, you would tell him collect more data. What is the effect of collecting more data? His curve will get narrower. Look, the entire problem with a curve or an interval like this is that it's way too wide. I wish it was just a little bit narrower. So how do you make it narrower? You tell him collect more data. He'll eventually become narrower and he'll look maybe something like this. Thus, removing this problem here, right? This person eventually the thing that he'll be told is that your confidence interval is a bit wider than expected, and it's making it difficult to make a judgment call. It looks as though you might not have an important effect because your mean is less than the specified number. However, you do have some values beyond that number. For that reason, we suggest that you collect more data. That is how it's formally given, right? And you know, I kind of went really fast on this. Can you repeat the importance point, please? Yes, of course I will. Don't worry. Just wait 2 minutes for everyone to come back. Then I'll redo this again because I feel like I did it really quickly. Now, someone asked how many lectures am I doing today? Now, ideally, I'd finish this lecture, and then the hypothesis testing lecture, and then the comparison of means lecture, and then the ANOVA lecture. And that should be enough for today. And the rest will be covered by my colleague Harun. And yeah, so today I hope we can finish all those lectures. We might take more than 8:30, especially I was not expecting that we would. Yeah, I was not expecting we'd take 2 hours on the first lecture. So yeah, the problem is this is the hardest lecture. This is the easiest of all the lectures. So I can imagine we'd spend more time on the rest, right? May we go over slide 21 real quick? So slide 21. Yeah, this entire slide talks about the next lecture. So, you're not going to understand anything if we just talk about this. You need to actually see the figures in the next lecture. And when we talk about the next lecture, when you go back on this and read it, it will start making sense to you. Okay? So I will advise that we just go to the next lecture after we review these last few lectures. These last few. Oh no, I accidentally ended this lecture. No, the sharing screen. God damn it, dude. Someone has a picture of a. Is that a koala or? Okay, so it's 5:30. I accidentally closed the lecture, so that's always good. There's the Zoom meeting, share screen, and this, and then get chats. And then this chat should stay like that. I've got a question we had in the midterm. If you could show us how to solve it at the end, that would be great. I won't send it now. Let's finish this first. Okay, I would appreciate that because I was expecting we would finish this lecture by 4:30. I was surprised that this lecture, the easiest one, we're finishing it in 2 hours. So I expect that we're going to take quite a while until we finish everything. At the very worst, we might take an hour tomorrow just to finish the last lecture, which is ANOVA. It's simple. It's not. It would take an hour to finish it, but for now, let's just focus on finishing hypothesis testing and comparison of means. Then we'll see what we'll do with ANOVA. Maybe I think it's better if we take more questions than I just plop all these lectures on top of you, right? So I think it's better if we focus on. By the way, is someone recording? Okay, yeah, someone is recording. Okay, good. Just wanted to make sure. Uh, okay, so everyone's here. Now I know what you're all thinking. I went way too fast on these points. I agree with you. So we're gonna redo some stuff. I accidentally saved all of this. So now if I press erase, it won't erase. It's fine. We can do it. So A goes from here to here. Now I already did all the answering, so I want you guys to answer, and I'll see why some of you might be answering wrong if you answer wrong. So A, here's the question: is it significant? Once again, this is the mean, and this is the importance cut. This is the importance. So A, you're all saying it's significant. I agree with you. It's not touching this mean, so therefore it's significant. Now, is it important? Yes, and important. I agree with all of you. Okay, so now let's go to B. Whoops. Okay, let's go to B. So now, is B significant? Okay, and is B important? I would accept that if some of you said it's likely to be important. However, collect more data for us to try. Yeah, exactly. Try again. So it could be important. It's since the mean is leaning towards this side, not this side, not down here. It's more here. It could be important, but just to be sure, collect more data. You'd eventually may get a narrower confidence interval, and you might look something like this, just a bit narrower. Like you might look something like this, right? And then this would be considered like A. So C, what do you think about C? Is C significant? Yes, it's significant. Okay, and I know you're all seeing this this right here, but yeah, whatever. So it's fine. You can cheat if you want. Say you all get the idea. Now is C important? How do we know if it's important? This line, you see this line where it says here important. If you're beyond this line, it's important. So yeah, this I agree with all of you. It's probably not important. He probably just cheated and got a lot of people in a study, and he proved significance, but didn't prove a really high effect size. So what about D? D, is it significant? All of you are going to say no. I agree with you. Now, is it important? You really can't say. You got to tell them to get more data, right? It's inconclusive. So I agree with this. Now, what about E? Is it significant? No. Okay, and is it important? No. So yeah, see, just by looking, you can already tell a lot, right? Just by looking, you can tell about significance. You can tell about now for all of them. Can you calculate the p-value? No, you can't calculate a p-value. Now here for this confidence interval, this confidence interval had a 95% chance of hitting the sample mean. Is this true? Of hitting the sample mean? Is this true? No, it has a 100% chance of hitting the sample mean. See, these are all the tricks. I'm just revising confidence interval in general for all of you, right? What if study B happened to have less sample size in the next study? Would it look wider or narrower? Wider. See, these are all theoretical concepts that he might ask you in the exam. So I'm just revising it really quickly. Now, this is the same. This is the same, right? The only difference is that it's horizontal now instead of vertical. So here, is this significant? This is the mean that we're comparing to. This is the importance. Anything to the right of this is important. And he tells you here, difference greater than 10. So is this significant? Yes, of course it's significant. Not touching this mean. Is it important? No, it's not important. It's not going beyond this line. What about this one? Is it significant? Significant, both. It's both. It's significant and important because it's not touching the mean and it's beyond this line. What about this one? Is it significant? Is it important? No for both, right? It's not significant or important. What about this guy who covers everything? You would tell him to collect more data because right now it's inconclusive, right? His mean is slightly below, so I expected maybe it will end up looking something like maybe B. But the idea is that, hey, why isn't C significant? Because it's touching the mean. Remember, we were saying that if it touches the mean, you say that the p-value is more than 5%, and p-value more than 5% is not significant. Um, yeah, and D is just, it's not. You tell him to collect more data. You really can't say much. You gotta tell him to collect more data, and then his curve will get narrower. And I'm just saying all of this, but all these slides, all of these, yeah, it has a low power. But we'll talk about power more in detail. All these slides, you'll see that there's like text. All that I talked about is in here. So I'm not going to go over it, right? And the same thing over here talks about all the things that we talked about, right? Here's just C and D, comparing C and D, this one and this one, but we already talked about it. Here, they're giving you this idea that when you have a really wide confidence interval that's covering everything, what do? It suggests that more data needs to be collected, right? Yeah, I didn't get that. Yeah, look, if you didn't get power, it's fine. But basically, the wider a confidence interval is, the lower the power. And I want you to memorize that for now, because this is not where we're going to talk about power. We're going to talk about power in the next lecture. But you all understand this, right? So confidence interval should be your game, right? Confidence interval should be something that you all now are pretty much golden with. I hope so, right? So before we go on, do you guys have any questions on confidence interval? I don't want to see any question about power. I don't want to see questions about hypothesis testing. I don't want to see questions about, oh, there's something mentioned in the slide about type 2 error. Like someone asked a question about this slide. This slide, the majority of it is from hypothesis testing, right? On the basis of what the p-value is, if it's more than 5 or less than 5, we make a decision on whether to reject or accept the null hypothesis. This is purely the next lecture, and even under it about type 2 error. Sorry, where's my cursor? Even everything under it about type 2 error. This is all the next lecture. Confidence intervals help determine whether this type of error can be made. Again, all this talk about errors is about the next lecture, not about this lecture. And then he talked about the magnitude of interest, and I explained this, using the whether it's important or not important, right? The significance level, not the significance, the effect size, right? Narrow confidence intervals are better because we're more confident that the mean lies in a narrower range. Yeah, you can sort of understand it like that when you have a narrower confidence interval, you're more confident. You're more confident that the true population mean lies somewhere here, and you can trust a narrower confidence interval. That suggests that it has a strong power. Now, what does power mean? I'll just quickly say it. Power means that if there was a difference, the higher power means that there's a higher chance you'll detect that difference. So for example, your study might be amazing, but the power might be 50%. That means if there was a difference, there's only a 50% chance you'll find it, which is terrible, right? Most studies would like a power of 80%. 80% is kind of like if you hover somewhere around that, that's a good power. That means if there was an effect, if there was a difference, there's an 80% chance that you might find that difference with the study, which is good. It's indistinct of the 95%, indistinct of it doesn't have anything to do with those things. You'll see later that it's linked to something else called beta, called the type 2 error. We're jumping ahead. Difference in one. Okay, so an 80% chance that there's a difference between two different groups, for example, a group taking placebo versus a group taking dopamine. You gave an example. I don't remember. Okay, so while you're remembering it, we'll talk about widening. I don't get the power part. Yeah, you're not supposed to get the power part. It's next lecture. Does anyone have any question on this lecture about the widening example? This B, this one. If this study, instead of having a sample size of, for example, 16, had a sample size of 8, what do you expect will happen to the confidence interval? Will it get wider or narrower? Wider. I agree with you. It's going to get wider because this is the idea that we said in the beginning. So as your n decreases, you're going to get wider confidence interval. As it increases, it's going to get narrower. That's the example I was mentioning. So this lecture really doesn't have that much in it. It has some theory, a lot of concepts. Can you explain what exactly the null value is? Okay, look. When you're in the hospital, okay, there is a standard that has to be held. There is a standard that is different from every single hospital. But when you're in that hospital, if you're in the infectious diseases department, if you're in the cardiology department, if you're in the ICU, there's always a standard, there's always a guideline, there's always a protocol. So if you're in a hospital and you hear someone say, "Oh, we're going to give him furo and his cat is like 3.2 or something," you might look and say, "What the hell are they talking about?" But they exactly know what they're talking about because they're used to the standard of talking. They know what furo is. They know what kriat is. They know this stuff between them, And this is the same principle with biostats. With biostats, one sample might have a mean of 100. One sample might have a mean of 200. One sample might have a mean of 300. One sample might have 400. One sample might have 70. One sample might. Instead of overloading everyone every single time with numbers, what they generally agree on is that when you get a sample, like let's say it's 70, change it to 0. And then whatever other sample you get, just mark the difference. I don't want to care if your sample is 400 and that guy's sample is 200 and that his other sample is 220 and that his difference is 20. Just write it as 0 and 20. This is just convention. This is just the thing that this is the same thing when you're in the hospital and they tell you, "Oh, we're in the ICU and we gave him furin." This stuff, they don't want to hear that, "Oh, by the way, we gave him IV furosemide dose of 40, whatever." They don't want to hear excess stuff because that's where confusion happens. That's where, like, especially when you go into residency or stuff, you should expect a lot of hectic work. So the last thing you want to hear is someone overloading you with so much information. Just like, come on, talk about the standard stuff. Just be quick, be quick. Same thing with biostats. We don't want to hear that the sample is 100 and then your other sample is this. No, just put your sample as 0 and then whatever sample is like 20. Good, good. Okay, perfect. That's what null value is. Okay, so I think this lecture is good with all of you. I kind of am a little upset that we needed to spend 2 hours on it, but let's see. Don't save. Oh, I forgot to put I keep forgetting to put the break picture up. Next break, I'll remember, inshallah. Okay, so what was the next? Yeah, hypothesis testing. So welcome to hell. Absolutely welcome to hell, okay? I'm sorry. I know you should always say, "Oh, hey, don't scare us, whatever, blah, 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 blah." No, this is the hardest lecture. It takes like also 2 hours to finish. But